Okay, hopefully this demonstration should build on what you just saw in the lesson and help explain how transformers work, which is what the rest of the homework's on. So, very quickly to recap, we've got a coil of wire with quite a lot of turns connected up to a very sensitive ammeter. And just to show you what we've already seen, if the field inside the coil changes, for example by bringing a magnet near it, let's get this on the right scale, for example by bringing a magnet near it or taking the magnet away, whenever the field inside the coil changes, a voltage and therefore a current is induced. The faster that change happens, the greater the voltage and current. So if I do this slowly, you'll see a small deflection. If I do this quickly, well, wasn't that convincing, was it? Slowly, small deflection, quickly, larger deflection. So that's that. We've seen that. I'm just going to put an iron bar in the coil just to make the field inside the coil stronger, to make it easier to measure on the ammeter. Now, you've also seen what happens if we put a coil of wire next to our other coil of wire and pass a DC current through it, and you'll see on the ammeter that the current is DC. Now, when I turn the current on, we get a large deflection on the ammeter over here in this coil, but then that deflection goes back to zero very quickly. So when the DC current is switched on, this coil becomes an electromagnet. That creates a magnetic field going through the iron bar and going through this other coil. So the field inside this coil changes. As the field inside that coil changes, a voltage and therefore a current are induced. But once the current is set up and once the field is set up, the field is no longer changing, so there's no longer any voltage or current induced. If I switch the electromagnet off so the magnetic field disappears, that's another change in the field inside this coil. And if the field changes, a voltage and a current are induced. So you can kind of make a crude sort of AC by switching the current on and off. Obviously there'd be a nicer way to do that, and that would just be to use AC on this coil in the first place. So if I replace my DC power supply with an AC power supply, now take a look at the ammeter on the right. This is the supply going into the coil on the right. Now the current, zero, is here, okay? So the current is changing, it keeps changing direction from plus 1 amp to minus 1 amp. No, actually, sorry, that's plus 0.2 amps to minus 0.2 amps. I read off the wrong scale. That's an alternating current going in. That means that our electromagnet here is constantly producing a magnetic field. Then the magnetic field goes to zero. Then it produces a magnetic field the other way. Then it goes to zero. Then the other way. Then it goes to zero. It's constantly changing the magnetic field. Therefore, the magnetic field in this coil is constantly changing. And if you look at our ammeter over here now, you can see that we're getting, I might just click it down a notch on the sensitivity. That fits on a bit better. You can see that we're getting an AC current coming out. So it's an AC voltage induced in this and an AC current. I'll click it back up because it's more impressive that way. Now, this is basically how a transformer works. You've got a primary coil here, which you feed AC into. You've got a secondary coil here, where AC is then induced. Now, these are the only two coils I've got. But I'm sure you can imagine that changing the number of coils on this, the secondary, will change the voltage. Okay? Because we know that if you've got more coils here, you're going to get a greater voltage induced. So if we have more coils here, we get a greater voltage. We can actually get a greater voltage out than is put in. So if the number of coils turns on this coil is greater than the number of turns on this coil, we get more voltage out than we put in. Now, you might be worried that that's happening. You might be worried that we're getting something for nothing. As we discussed in the lesson, you can't get something for nothing. Anytime you're getting energy out of a system, energy must be going in. And in this case, if you're getting more voltage out, that means you have to be getting less of something else out. And as you'll read in the textbook, the thing you're getting less out of is current. So if you have end up with a bigger voltage at this on this side of the transformer, you end up with a lower current, and the product of the voltage and the current, which is the power, is the same, assuming that the transformer is very efficient. So this is essentially how a transformer works. We've got AC going into a primary coil. That creates a changing magnetic field, and the changing magnetic field exists in a secondary coil, so a voltage is induced in the secondary coil. And by changing the ratio of the number of turns, we get different voltages and currents. Now, the bit of iron is quite important. Notice what we've got here in terms of the induced current. If I were to take the iron core out, I imagine it's going to be significantly less. In fact, it's barely discernible. So the iron core is really important, and with a transformer, you'll have an iron core that wraps all the way around. I'll show you one actually. You'll have an iron core, this one's made of 2 parts, that actually wraps all the way around. So the field lines go all the way around the core when you've got a proper transformer. So I hope that video has helped and will help you with your homework, just to get across the key idea of how transformers work. They are amazing, so that is how electricity is transmitted across the national grid, by changing the voltage, either stepping it up or stepping it down. You've already studied that with the national grid. It's done with transformers, and this also explains why we need AC for it to happen, because this didn't work with DC. Okay, with DC we just got one pulse out the other end when it was switched on, and one pulse when it was switched off. If we want continuous voltage, a continuous output at this end, we've got to put AC in, and then it turns out we get AC out. Excellent. Right, that'll do. I hope that helps you with your homework.